Bismillahirrahmanirrahim. This is part B of lecture 6 on Descriptive Statistics and Islamic Approach. In this lecture we will discuss some of the basic tools required for a real statistical approach. The basic element of the approach to statistics developed by Fisher, which is currently the sole approach available, imagines an infinite population from which the data is a random sample, and this infinite theoretical population is characterized by a few parameters. This assumption we remove because it's just basically for computational convenience alone, and instead the fundamental tool of the real statistical approach is the actual data distribution, which depends on all 15,000 points. Every one of them determines the data distribution. The picture of this data distribution is given by the histogram, which we have discussed. A mathematical development requires the use of empirical cumulative distribution function, which we will deal with in a later stage. Now, this is the basic, and then there are summary statistics which are used in Fisher's approach. Normality is the key, so the summary statistics are the means, the variances, and the standard deviations and correlations. None of these are very useful if the distributions are not normal, which is normally the case. Now, in the real statistics, the basic summary statistics are the quartiles, which are a natural description of this data set. And this is what this lecture will deal with, explaining what the quartiles are. So here's a picture of how we calculate the quartiles for a data set. First, we sort the data from the smallest number to the largest number. And this can be done with a click in Excel. Then we divide the data into 4 parts of equal size. So then the very bottom, the smallest data, the minimum value, we will call Q0, the 0th quartile. The first quartile is the number which divides the smallest 25% from the next 25%. Then the median is the portion which divides the data into 2 equal halves. One half is below the second quartile or the median, and the other half is above the median. The third quartile divides the data into about 3 parts below and 1 part above. And the fourth quartile is the maximum. So this basically gives you a shortcut picture of the data with only 5 numbers. To illustrate how these concepts are used, we demonstrate them on the HISE data set, the Household Income and Expenditure Survey. This is a data set with 15,509 observations on the household size and the household expenditure per capita. The data is, we arrange the data using Excel from the lowest to the highest. So this is for the household size. So the smallest household size is 1, and that's the Q0, that's the minimum household size. Then when we go up, we have a list of 15,509 numbers, each of which is a household size. So when we go up to about 3,877 element household, this 3,817 is about 1/4 of 15,509, the total number of households. So at the quarter position, the household size is 5, which means that 5 is the first quartile, and 6 is the median household size, which means that the number of households from 1 to 5 is about half, and the number of households above 6 is also about half of the data. 8 is the third quartile, and the maximum is 60. So the summary statistics are 1, 5, 6, 8, and 60. 1 is the minimum, 5 is the first quartile, 6 is the median, 8 is the third quartile, and 60 is the maximum. So these are the summary statistics for the household size data, 15,509 numbers from the HISE data set. It is much easier to understand numbers when they are put into a picture, and the box plot is a way of picturing the summary statistics. So here is a box plot which shows these same household size summary statistics which we discussed in the previous slide. The minimum value of household size is 1. The first quartile is 5, and that's where the box starts. So this is also called a box and whiskers plot. So the whisker goes from the minimum to Q1, it goes from 2 to 5, and then there's a box which goes from 5 to 8, the Q1 to Q3. So in this box is half of the data. Outside this box, below Q1 you have 25% and above Q3 you have 25%. And then inside the box you draw the median line. The median line occurs at 6, which means that inside this box you have half of the data, but between 5 and 6 you have one half, and between 6 and 8 you have the other half. So this data is not symmetric. So we see that the data has a spread from about 5 to 8, 5, 6, 7, 8. These are the size of households which have half of the population. This is an asymmetric distribution. It's right skewed because to the right we have a longer distribution. It also has a short left tail, that's the whisker on this side, and it has a very, very long right tail. The 61 value for the maximum household size is not even on the plot because it's so far away. Because the household size increases by integers, there are some difficulties in exactly matching the definitions of the quartile. So if we look at household size, 5 is the first quartile. If we look at household size of 1, 2, 3, and 4, this consists of 3,412 households, which is about 22% of the data, not 25% as would be the case for. That's because some households of size 5 have to be included in this count in order to come up to the 25%, which is the definition of the first quartile. Then if you go up to households of size 6, you get to 35%. So basically within the category of 5 you have about 13% of the data. So if you take some of these 5 count households and put them into the first quartile, you will get up to 25%. 6 is the median, which means that when you go up to 7, the number of households with size below 7, 1, 2, 3, 4, 5, and 6, is 50.9%. So it's more than 50%. So that's why 6 is the median. And similarly, when you go up to 9, you have 75.6% of households below 9, which means that 8 is the third quartile. Lack of exact match between the quartiles and the 25%, instead of 25% we had 22%, occurs because the household size is a discrete variable. It jumps from 1 to 2 to 3. Unlike this, the total expenditure per capita, this is a continuous variable. So because of this, you get the correct picture of the quartiles in this situation. Now it turns out that the minimum value of the total expenditure per capita over all of these 15,000 households is 1,966 rupees expenditure per person. This is the smallest in this all 15,000 points of data. So this is the minimum value. The first quartile is 14,275. So this means that about 1/4 of the households had expenditure below this amount, 14,275 rupees. If you calculate exactly, it turns out it's 24.998% of households are below this value. Now, if you take 14,275, this will go slightly above 25%. And that's exactly what we mean for the first quartile. The median is 19,454. Below this value, you have 7,754 households, which is about half of the data set. So about half of the households have total expenditure per capita below 19,454, and half of them have above this number. Then 20,645 is the 648 is the third quartile. The picture of this data is in the box plot. If you look at it starts at 1966, although the point is not marked. So whisker goes up to 14,275. That's where the box starts. This is the first quartile. Then the box ends at the third quartile, which is 11,631. Sorry, The third quartile is 28,648, and the median value is 19,000. If you look at the box, you see that the median is to the left of center, and the box is longer on the right hand side, which means that this distribution is right skewed. Also, the maximum value of the income is very, very large. So this has a very, very long right tail, and it's a skew distribution. So what do we learn from these summary statistics? We learn about the center of the data distribution, which the point which divides the data into two equal halves, one below and one above. We learn about the spread of the data. How spread out is it? That's the interquartile range. The distance between Q1 and Q3 is the size of the box is taken as the how much the data is spread out. We look at the symmetry. If both sides Q1 and Q2 are balanced around the center, then this data is symmetric. In our case, both of the cases, the data has not been symmetric and it has been skewed to the right. And we also get to look at the tails of the distribution. How long does the data go on after the middle? So all of these are very important characteristics. In our case, we are looking at the exact actual data distribution, unlike the Fisherian case, which uses all of these characteristics, but those of an imaginary theoretical distribution. In Fisherian statistics, the center of the data is the average or the mean. This is a very good statistic for the normal distribution and a very bad statistic for other distributions. So in real statistics, since we're dealing with actual data distributions, we will always use the median as the center of the distribution. The median in total expenditure per capita is 19,454. Exactly half of the households are below this number and exactly half are above this number. It's a very natural and intuitive summary statistic. The summary statistics also explain to us how widely spread out is the data. So the first measure of this, called the interquartile range, this goes from Q1, which is first quartile 14,275, to 28,648. The difference between these is about 14,193, and this is called the IQR, the interquartile range. This is a measure of dispersion. But actually we have more information about dispersion, and that's also refers to the tails. In this particular case, for the incomes, we know that the right tail is extremely long. The maximum value is 1 million something, and it's very large. On the right side, there's a short tail. So this also tells us something about the dispersion of the data. These are replacement for the standard deviation measure, which is very good for normal distributions and terrible otherwise. We've already seen that household size and household total expenditure per capita are right skewed. The total expenditure per capita is much more right skewed than the household size, and both have large right tails. The household size right tail goes up to 61, the maximum household size. The TE total expenditure per capita tail goes to 1,268,708, and this is a much longer right tail. The normal distribution, by contrast, is symmetric and has very thin tails, so it could never be used to characterize these distributions. Now we introduce the median line of x given y. This is a replacement for the regression lines created by Fisher. David Friedman, a famous statistician, said that we have been running regressions for about a century, and this has not led to any useful results. Let's abandon this technique, and this is exactly what we propose to do here. Regressions are based on a large number of assumptions, none of which are valid in real data sets. So here is the alternative. First, we classify the variable y into short ranges like bins in a histogram. Then we compute the median value of x for all the values of y within one bin. Then the median line graph tells us how the median of x changes as y changes. There are two median lines, the median line for household size given income and the median line for income given household size. So they are x given y and y given x. So here's the median line of total expenditure per capita for each household size. So it's important to understand what this graph is. The first point is obtained by looking at all households of size 1 and then calculating the median total expenditure per capita, and that turns out to be around 60,000. Then we look at all households of size 2 and we calculate the median income for all households of this size 2, and this is now around 35,000. And then we look at all households of size 3 and we calculate the median income. This comes out to 30,000. This median line divides the population into two halves. One half is above the line and one half is below the line. As we see that initially, as the household size increases, the average income, the median income, comes down quite rapidly. But then later on, around household size 10, for example, it stops decreasing and it just becomes flat. So this median line gives us a very good idea of the relationship between the household size and the total expenditure per capita. Going in the other direction, suppose I want to make a median line of household size for total expenditure per capita. Now total expenditure per capita is a continuous variable, so I have to divide this into small buckets just like we do in the histogram. And what we would like to do is to keep each bucket of roughly the same size. So there are about 15,500 observations. So if I want to create 20 buckets, I will put 775 people into each bucket. So suppose I sort the data by total expenditure per capita in sequence and put 750 or 775 households in each bucket. Then I create 20 income groups, each according to the 775 members. And then I calculate the median household size for each of these income groups, and then I plot to get the median line. The details of this procedure: the first step is to create the income buckets. 1966 is the smallest income. So when we go from 1966 to 9,614, there are 775 households in this. So basically, the first income group goes from 1966 total expenditure per capita to 9,609, and then the second income group goes from 9,614 to 11,220, and the third group goes from 11,221 to 12,324, and so on. Each of these groups has about 775 or 776 people in it. So that's how we choose the sizes of the groups. So now we have income groups. Then for each of these income groups, there are 775 households, and we can calculate the median household size in these groups of 775 people. So here's the picture of the median line. In the smallest income group, the median household size is 9. Then in the next 4 income groups, the median household size is 8. And then in the next 4 income groups, the median household size is 7. In the next 5 income groups, the median household size is 6. In the next 5 income groups, the median household size is 5. And in the last, the richest income group, the median household size is only 4. So this shows clearly that as the income increases, the median household size comes down, and this shows the basic thing that we wanted to check to see if rich people have fewer children. So this data clearly shows that this is true, but note that the median means that half of the households are above and half are below. So this means that in general there is a tendency for wealthier families, wealthier households to have fewer children. But this tendency doesn't mean deterministic. There might be very wealthy households who have very large number of children, and there might be many poor households who have very few children. It's just that the median is going down. In this lecture, we have studied the relationship between total expenditure per capita in households and also the household size, and we have found that there is a negative relationship. Notice that you had to choose the variables correctly. Total expenditure by themselves do not work correctly in this context, and there were reasons to understand that it should be total expenditure per capita, which is the proxy for wealth. We studied how the household size changes as income rises, and we saw that household size decreases. Similarly, if we study how income changes as household size increases, we see that the income decreases if household size increases. These show the association between these two variables. They do not tell us the cause. Is it true that the increase in families leads to lesser income, or is it true that when people have higher income they have smaller families? We don't know which direction, and it could be that there is some third cause which leads to both higher incomes and smaller families. Something like education leads to higher income and leads to smaller family size. So the causality cannot be directly understood from the data, but it is very important to understand, and we will study this in greater detail later.